part of the video series of Understanding Genetic Tools, we'll be looking at interpreting breeding values. So first up, what are breeding values? Simply put, a breeding value describes the genetic merit of an animal, so it looks at the genes that it will pass on to its progeny. So for sheep in Australia, we have ASBVs, or Australian Sheep Breeding Values, and in cattle, we have EBVs, or Estimated Breeding Values. Regardless of the species or breed, its breeding values are a national method to compare the genetic performance of sheep or cattle. They take into account performance information of the individual animal, but also relatives, as well as looking at the heritability of traits and genetic correlations between traits as well. And they go hand in hand with visual assessment and help you improve your selection accuracy and breed better livestock into the future. So let's take a look at the genetic analysis pipeline. We get data from three key areas. So we have our information that's been previously submitted into the evaluation, so our evaluation database. We also get data sent in from on-farm, so stud-stock breeders that collect performance information, but also relative information, so sire, dam, and half-sibling information as well. And then we also get information from research flocks or herds, so that comes through our research database pipeline. So from all of these different pipelines, we have information on individual animals, so how they perform themselves, as well as how their relatives perform. Any relationship information, so looking at the sire and dam in pedigree and filling that back pedigree as far as we can. We then look at individual trait heritabilities as well as genetic correlations between traits. We also utilize genomic relationship information and also account for environmental information in the analysis as well. In the analysis, we also adjust for any known non-genetic impacts on performance. So these can be things like the birth and rear type of an animal, how old that animal is in days at any given measurement, so any performance or phenotypic performance measurement. I mentioned we adjust for environmental influences, so we look at how much an animal's been fed or the nutrition differences, health status differences, and management differences between animals. And then we also make adjustments for the age of animals' dams as well. So in sheep, we recalculate breeding values every 2 weeks. In cattle, that's a little bit dependent on each evaluation. So it's always really good to have a look at the date of that breeding value to make sure that you're looking at the most up-to-date information when you're looking at animals' breeding values. And then once we've run through the entire analysis pipeline and calculated breeding values, we report hundreds of individual breeding values which are relevant to lots of different production systems. So let's talk through what a breeding value actually looks like. We always report 4 key pieces of information. So we've got the age stage, the trait code, the breeding value, and the accuracy. So let's dive into this a little bit further. The first bit is the age stage and the trait code. So for every breeding value, you'll always be given the trait that you're looking at, as well as the age. So for this particular example, we're looking at the breeding value PWT, or post-weaning weight. And I know that it's post-weaning weight because the first letter symbolizes the age stage. So that can be birth, weaning, post-weaning, yearling, hogget, or adult. And then the last few letters after that age stage symbolizes the trait code. So WT means weight. We then have the actual breeding value itself. So for this example that we're looking at for PWT, the breeding value is positive 10.2. So we report breeding values sometimes as positives, sometimes as negatives. And we'll get to understanding which is better a little bit later when we talk about percentile bands. But the key thing to think about is that we do have positive and negative breeding values. It's just the direction of that breeding value from the average. So it's always really important to consider the direction that that breeding value should be going in, essentially. And then we also report an accuracy. So an accuracy, the accuracy, I guess, shows us how close that estimated breeding value is to the animal's true breeding value. So a high accuracy will indicate that there's more information being utilised in the calculation of that individual animal's breeding value. So it just reflects how much information is actually being used in the analysis. In sheep, we report breeding values across 5 key trait groups. So we've got growth traits such as live weights, adult weights, We have carcass and eating quality traits like eye muscle and fat depth, intramuscular fat, lean meat yield, dressing percentage, etc. We have wool traits, which are for fleece quality and quantity. We report reproduction traits, so things like weaning rate and its components, being conception, litter size, and rearing ability. And then we also report health traits as well, so things like worm egg count and breech wrinkle. Likewise, in cattle, we similarly report key trait groups. So we've got growth traits like birth weights, milk, 200, 400, and 600 day weights, as well as mature cow size and weight. We report growth and eating quality traits like carcass weights, eye muscle area, intramuscular fat, and marbling. Reproduction traits such as scrotal size, days to calving, percent normal sperm, as well as behavioral and structural traits like structural soundness, docility, flight time, etc. So how do we actually use breeding values in practice? If we turn up to a sale or we're looking at a catalogue and we've got two different rams that we're trying to decide, whether you want to purchase or make a decision between, it's a pretty simple process to figure out how different the genetics is between these two sires. So we've got ram A, which has a P weight of 11.8, for example, and then ram B, which has a P weight of 7.0 kilos. So our first step is to find the difference between these two. So we're going to take 7 kilos from 11.8, and that gives us a difference of 4.8 kilos. Then we're going to divide this difference by 2. So we assume that on average, a progeny will inherit half of its genes from its sire and half from its dam. So that's why we divide by 2. So we're going to take 4.8 kilos, divide that by 2, and that gives us a 2.4 kilo difference. And that ultimately means that sire A will go on to have progeny that are on average 2.5 kilos heavier at post-weaning than sire B. So that means that sire A's progeny are going to be heavier at post-weaning age just through selecting better genetics, not through feeding them differently or managing them differently. That's just from genetic selection. So I mentioned previously that negative breeding values aren't always a bad thing. So it's really important to, I guess, consider some key things when we're looking at breeding values. As I said, negative breeding values aren't always a bad thing. We have to consider the direction of the breeding value in context of the trait. So if we look at this Angus bull example, a Hereford bull example, we have net feed intake on the far right-hand side. Its breeding value for net feed intake is negative 0.10. So in this particular instance, net feed intake is actually a more positive direction than a positive feed intake. So that's a good thing. So just remember to think about the direction of the breeding value in context of the trait. The other thing that's really important when it comes to breeding values is where that actual value, so where the ASBV or the EBV, sits relative to the percentile bands. So a percentile band shows us the spread in industry at a particular trait. So what the range in performance is for all animals in that evaluation for that particular trait. So if we have a look at gestation length, which is the third trait in from the left-hand side here, that particular bull has an EBV of minus 4.4 for gestation length. And it's actually showing us that that's in the top 7th percentile for industry. So the EBV value is important, but also where it sits relative to industry is really important to think about as well. The other thing to consider when you're looking at breeding values is how that particular trait is expressed. So we have a range of different traits that we produce breeding values for, and they are obviously range in their units of expression. So for this particular bull's example, we have traits that are expressed in a percentage, in kilos, in centimeters, and millimeters, for example. If we have a look at the sheep percentile bands, just quickly wanting to run through this one as well, we report, you can find these on the Sheep Genetics website or in sale catalogues. So very quickly, we've got our percentile bands on the left-hand side, and then up the top, we've got our individual traits. So this particular example is looking at our terminal percentile bands. So if we focus on the top red highlighted box, which is under the PWT column, That's highlighting a breeding value of 18.09. So that's saying that that particular breeding value is the cutoff for the top 5th percentile of industry. So we know that if the breeding value for PWT or post-weaning weight is above 18.09, it's going to be in the top 5th percentile for industry. So again, it's really important to think about where that actual value of the breeding value sits relative to industry, because you could look at a PWT of 10 and say, oh, that's a good number. But really, when you then put it in context of the entire spread in industry, it's actually performing in the lower percentiles. Another thing that we report as part of our genetic evaluations is indexes. So indexes are a nice handy tool to help you, I guess, refine your selection decisions because they combine lots of individual traits into one particular value. And they also consider genetic correlations between those traits. And then they also weight those traits at a given economic weighting based on how important they are to a particular production system. So if we have a look at the Merino Select indexes, for example, we've got 4 different indexes that we report in our Merino Select analysis. So our fine wool, our wool production, our sustainable merino, and our merino lamb index. And each of these indexes have pretty similar traits that they are made up of. So we've got all of the traits in the left-hand side of the column of this graph here. How they vary, though, is that relative economic contribution that I was talking about. So if you focus on fleece weight and fibre diameter, for example, fleece weight and fibre diameter have a significantly higher economic contribution to the FW index compared to the ML index. So if you, for example, or your client got a lot of their profit from selling wool and selling wool at a nice fine micron, then utilizing the FW index compared to, say, for example, the ML index would be more beneficial in helping make your selection decisions. So I mentioned that we can use an index as a nice, easy drafting tool. So how this works in practice is for any given list of sires or sheep that you might be wanting to either purchase or join from, you'd rank those animals from highest to low on index. So you'd sort them from highest to low on index, and then you'd go through and perform any culls based on structure or type of animal, remembering obviously that breeding values should be used in conjunction with visual assessment and structural soundness. And then what you should get is a cut down list of animals to potentially either purchase or join from. So if we have a look at the 3 rows of individual animals up the top right hand side of the corner, they've all got a very similar index value, for example. So that's where you use your index as a drafting tool, and then have a look at the individual traits for those individual animals from there. So for example, you might pick the 3rd animal down because you're aiming to improve, for this example, clean fleece weight and also breech wrinkle as part of your overall business directional breeding objective. So do breeding values actually work? We've gone through and we've understood what they are, how to interpret them, and how to use them in context. Do they actually translate to any difference physically if you're selecting animals for utilizing breeding values? So this validation piece was done utilizing some research data that we had in the sheep genetics analysis. So there was a research trial that had 300 commercial merino ewes, and those 300 commercial merino ewes were joined to 15 white Suffolk sires. Before any progeny performance information was entered into the analysis or recorded, they pulled out the highest 5 performing sires and the lowest 5 performing sires based on their post-weaning eye muscle depth breeding values. So the average of the 5 highest PEMD breeding value sires was 3.72 millimeters. And the average of the 5 lowest PEMD breeding value sires was 1.24 millimeters. So that gave an expected difference of 1.24 millimeters between the 5 highest and the 5 lowest sires based on breeding values alone. They then went and took progeny performance information And of those 5 highest size for their genetic merit, the progeny performed actually on farm had an average PEMD of 30.55. They then looked at the actual progeny performance of the 5 lowest size based on their genetic merit, and they performed at 28.5 mil. So that translated to an actual difference of 1.7 mils, where the expected difference was 1.24. So really, really high alignment between the estimated genetic merit of those sires and how their progeny actually performed. So if we take this example a little further and we can apply some assumptions to figure out essentially what the cost difference is between choosing a higher and a lower performing sire. So if we very simply just look at post-weaning weight, for example, we've got our RAM A and our RAM B examples here again. And if we apply some pretty conservative assumptions at a 45% dressing to sell lambs at $8 a kilo, that each of the sires is going to get 60 lambs and they're going to be used for 4 years, we can cost this out and see what the actual translational difference between purchasing RAM A is compared to RAM B. So again, remembering to find the difference between RAM A and RAM B, we want to take 7 kilos from 11.8 to find the difference between the two and then divide that by 2. So that gives us a difference of post-weaning weight of 2.4 kilos. We're then going to apply a 45% dressing to that, which gives us a 1.08 carcass weight. We'll then apply a conservative estimate of selling that at $8 a kilo, which gives us an $8.64 difference per lamb between sire A and sire B. If we then times that by 60 lambs, that gives us a difference of $518.40. And then if we times that by 4 years' time, that gives us a difference of RAM A producing a positive of just over $2,000 across a 4-year period compared to buying RAM B. But on top of that, it also means that you can hit your market weight earlier and also give your ewes a bit more time to bounce back before they need to get more lambs on the ground for you in the future. So as always, if you need some more information, please contact Sheep Genetics, either give us a call or send us an email.